Hey bro, what are you trying to mix?
I'm trying to mix oil and water.
See bro, oil and water do not mix. These are what we call as immiscible liquids. So immiscible liquids are those liquids which do not mix no matter how hard you stir it.
Oh, so what happened when we force them to flow together side by side through a narrow space? Will they follow pattern or will they fight? What will happen?
This is not a chemistry class question. It's a real life problem with a real life solution. So let's see what happens if we allow them to flow together through a narrow slit.
Hi everyone, I am Avish and this is my teammate Akib.
So now let's start with our project presentation. In this project, we explore the fascinating behavior of two immiscible liquids, think oil and water, as they flow together through a narrow slit, mimicking conditions found in microfluidic devices, porous media, or industrial pipelines.
But first, let's take a step back. Why study this? In industries like oil refining, pharmaceuticals, or food processing, multiple liquid phases often had to move through a tight space. If we understand how immiscible liquids interact under flow, we can design better equipments and we can generate a good separation techniques.
Now, now imagine a slit, a thin rectangular channel where both liquids are introduced side by side, one more viscous, one lighter, both having their own agenda. Do they separate neatly? Does one try to dominate other? Are there instabilities at the interface? That's what we are going to find out in the complete project presentation.
From a transport phenomena perspective, this problem is rich with interesting concepts. Viscosity difference, interfacial tension, pressure-driven flow, Reynolds numbers, and Remelin regimes. And when you combine these factors in a confined geometry like a slit, the fluid dynamics become very interesting. So
Let's
let's
dive
dive
into
into
the
the
flow
flow
of
of two
two immiscible
immiscible
liquids
liquids
through
through
a
a slit.
slit. So yeah, welcome to this video on the fundamental of immiscible liquid flow in transport phenomena. In this video, we will break down what immiscibility really means, how surface and interfacial tension comes into play, and why this topic is so important in the real world systems like oil spill, food emulsion, and petroleum pipelines.
When we say two immiscible liquids, we mean they do not mix. Even if you shake them vigorously, they will eventually separate again. A classic example, oil and water.
Why don't they mix? It's because of the molecular polarity. Water is polar, its molecules have a positive and a negative end. Oil is nonpolar. Water molecules love to form hydrogen bond with each other, but oil can't do that. So instead of mixing, they separate from each other to form two distinct layers.
Now let's talk about surface tension. This is a force that makes a water droplet from a bead. It's caused by molecule on the surface pulling together tightly. But when two immiscible liquids meet, we are talking about interfacial tension, the tension at the boundary between them. It's like two groups that they don't want to be mingled. They stay separated, minimizing the contact area.
So yeah, this divides a line which is called phase boundary or interface. It's not just a passive layer, it plays a huge role in how momentum, heat and mass transfer are transferred between the two fluids. In motion, this interface can stretch, ripple and even break down into tiny droplets, depending on flow speed, viscosity and geometry. That's where things get really interesting.
Miscible liquid flow is a far from lab only concept. Here are just few examples. Oil spills. Cleanup method depend on how oil spread and interact with water. Emulsions in food like mayonnaise or creamy or cosmetics, we temporarily mix immiscible liquids. Petroleum refining, crude oil often comes with water that needs to be separated efficiently. Microfluids, tiny droplet of immiscible fluids, are used for high precise diagnostic and experiment.
To wrap it up, immiscibility is all about molecular incompatibility, surface and interfacial tension define how these liquids behave, and the interface is the star player in how they flow and interact. Understanding these fundamentals lay the foundation of analyzing real world transport systems.
So there are foundational to understanding immiscible liquid interaction. So let me discuss about viscosity. Viscosity is a measure of a fluid internal resistance to flow or deformation. It tells us how thick or how sticky a fluid is. What it means? Imagine pouring honey versus water. Honey flows much slowly because it has higher viscosity. Mathematically, viscosity relates shear stress and velocity gradient. That is du by dy. Through it means tau equals to mu du by dy, where mu is a viscosity. Role in immiscible flow. In a slit of two immiscible liquids, each layer may have a different viscosity. That means u1 is not equals to mu2. The velocity profile becomes asymmetrical. The fluid with lower viscosity has a steeper and faster curve, while the more viscous fluid flows slower and has flatter profile. Viscosity determines how momentum is transferred between layer and across the interface. So our second property is density. Density is a mass per unit volume of a fluid and plays a vital role in gravitational stability, pressure distribution and buoyancy. What it means? Denser fluid, that is mercury for example, contain more mass per unit volume compared to lighter fluid, that is ethanol. It is a key factor in pressure variation with depth. P equals to rho gh, where rho is the density of the fluid. Role in immiscible flow. In horizontal flow, density has a minimal effect on velocity profile but can influence interface stability if acceleration or inclination exists. In vertical or inclined setup, the heavier, denser fluid tends to settle at the bottom due to gravity. If the denser fluid is above the lighter one, it can lead to Rayleigh-Taylor instability, unstable interface. Density difference are also key in phase separation and stratification. Our third property is interfacial tension. Interfacial tension is a force per unit length that exists at boundary between two immiscible fluids due to difference in molecular interaction. What it means? Just like surface tension at a liquid-air interface, interfacial tension exists at a liquid interface. It arises because molecules in each liquid prefer to stay with their own kind, causing a tension at the boundary. Role in immiscible fluid helps maintain a sharp and smooth interface between two liquids. High interfacial tension resisting mixing and deformation. Low interfacial tension allows more interface movement. In dynamic systems like pipelines, it determines whether the interface remains flat or undilute, whether the flow forms slugs, droplets, or wavy fields. Interfacial tension affects capillary pressure, which becomes crucial in microfluid system or a narrow slits. Our fourth property is miscibility versus immiscibility. This explains why some liquid mix while other does not. A key to understanding immiscible flow. Miscibility. Two liquids are miscible if they mix in all proportional to form a single homogeneous phase, that is ethanol and water. Molecular attraction between different species is stronger enough to keep them together. Immiscibility. Two liquids are immiscible if they do not mix and separate into two distinct phases, that is oil and water. Caused by different in polarity. Water is polar, oil is non-polar, no interaction, no attraction. The interface remains distinct with each liquid retaining its own property. Role in flow. Immiscible fluid does not chemically interact, but they do mechanically. Moment transfer via interfacial shear. Interfere behavior is crucial. It can slip, deform, or remain stable. Determine how energy is distributed between layers. Understanding miscibility is important in designing separator, extractor, and two-phase reactor. So now let us summarize all this. Viscosity controls the flow resistance except velocity gradient. Affect velocity gradient more viscous equals to slow flow, create asymmetric profile. Density affect the growth. Gravity related effect, pressure distribution and buoyancy can cause esterification and instability. Interfacial tension maintain interface shape, resist mixing, determine droplets or slug formation especially in dynamic condition. Miscibility governs whether liquid from one phase to or two immiscible flow have a clear interface and distinct mechanical behavior.
Laminar flow. Flow is smooth and ordered, with fluid layers sliding past one another. No turbulence or chaotic eddies occurs at low Reynolds number. Reynolds number is rho u h by mu, which is less than 2000. Fully developed flow. Velocity profile does not change along the flow direction, which is x, happens after the entrance region where velocity gradient settles into a stable shape. Mathematically, del u by del x is equal to 0. Implications: since the flow is fully developed and 2D, velocity is only a function of y. U is the function of y, that is velocity. Pressure varies only with x. The governing equations simplify significantly. Layered flow of immiscible liquid. Physical scenario. Two immiscible liquids, say oil and water, are fed into the slit and flow side by side. For example, this is the plate, this is the thickness of the slit. So the oil and the water will flow in this direction, and they are both they are mixed and they are flowing in this direction through this thickness towards the direction of this length. In steady low Reynolds number flow, the interface is assumed flat and stationary. This means no waves or mixing at the interface. Shear stress and velocity can be matched smoothly across it.
Now we will discuss the equation of motion. These equations are the fundamental in transport phenomena. The first is Navier-Stokes equation. The Navier-Stokes equation governs fluid motion, accounting for force like pressure and viscosity. For our case, we simplify it using assumptions. The first assumption is steady flow. Steady flow, it means there is no change in property of fluid with respect to time. The second assumption is laminar. The flow should be laminar. Flow is smooth, there is no turbulence in the flow. The third assumption is fully developed. It means viscosity profile doesn't change in x direction. It means du by dx equals to 0. The fourth assumption is 2D slit. It means the variation is in only y direction. And the fifth assumption is the fluid should be incompressible. Incompressible means constant density. What is the Navier-Stokes equation? The simplified equation is mu d square u by dy square equals to dp by dx, where mu is a velocity in x direction, mu is a dynamic viscosity, and dp by dx is a pressure gradient that drives the flow. We can apply the Navier-Stokes equation in the both the fluid, the heavier fluid and the which is at the bottom, and the lighter fluid which is in the top layer. So it should be mu 1 d square mu 1 by dy square equals to dp by dx, mu 2 d square u2 upon dy square equals to dp by dx. Our second equation is continuity equation. The continuity equation ensures mass is conserved in the flow for an incompressible 2D flow. Du by dx plus du by dy equals to 0. Simplification. Since flow is fully developed, it means du by dx equals to 0. So dv by dy equals to 0 equals to v equals to constant. Physical meaning. What is the physical meaning of that continuity equation? In slit flow, the vertical velocity component v is 0. So fluid only move in the x direction. Third is boundary condition. To solve differential equation from Navier-Stokes, we need boundary conditions. These are physical constraints applied at the wall and interface. The first is no slip at wall. At a solid surface, fluid sticks. There is no relative motion between fluid and wall. It means u equals to 0 at y equals to 0 and at y equals to h. Bottom plate y equals to 0, fluid 1 sticks to wall. Top plate y equals to h, fluid 2 sticks to wall. The second boundary condition is continuity of velocity at interface. At the interface, when y equals to h, both fluid must move at the same velocity. It means UH equals to U2H. This ensures the interface doesn't tear or slip. Physical, the fluid drag each other at boundary. The third is continuity of shear stress at the interface. The tangential force, that is shear stress at the interface, must be the same on both sides. It means u mu1 d u1 by dy at y equals to h equals to mu2 du2 by dy at y equals to h. This balances the viscous force across the interface. If shear was discontinuous, the fluid would separate or cause instability. The fourth is pressure gradient. Role. It is a driving force behind the flow, like tightening a pipe downhill or using a pump. Assumption. We consider a constant pressure gradient, that is dP by dx equals to constant. Sum for both fluids since pressure is continuous across the interface. Now, why this is important? It links back to Navier-Stokes equation and determine the shape and magnitude of velocity profile. So how all this thing assumption is fit to the Navier-Stokes equation? Solve the simplified Navier-Stokes equation separately for each region. Interact each twice. Get two parabolic profile. Use four boundary condition. The first one is no slip at bottom, no slip at top, continuity of velocity at interface, continuity of shear at interface. You will get the fully velocity profile for both fluid ready to analyze flow rate, interface behavior, etc.